In this video, we are going to perform an optimization under uncertainty for a large 53-bar truss. Now, in some of the other tutorials I've done, the size of the problem was relatively small. In some of the problems, I maybe used 2 variables. In another optimization under uncertainty, maybe I used 3 variables. But in this example, we are going to be going over a problem that has 53 uncertain variables. I want to walk you through the process, what that looks like, how do we minimize the number of black box functions. Today, the black box function happens to be MSC Nastran. On this slide, you see a comparison of 3 different configurations of the design model and their respective probabilities of failure. Here on the far left-hand side, we assume that the means of all the uncertain variables are equal to 0.01. We go ahead and we calculate what the probabilities of failure are, and we find out that there is a 0% chance that this mechanical system or structural system fails. We went ahead and did a MSC Nastran Sol 200 optimization where we assume that the responses are deterministic. There's no variability in the inputs. Here we find the optimal solution. It took 7 MSC Nastran runs, but the probability of failure was actually 66%, which is not good. Here the goal is to limit the probability of failure to 5%. So in this tutorial, we use Dakota or Sandia Dakota to perform this OUU. Here we have the optimal solution or the values for the variables. Here we find out that we needed 280 MSC Nastran runs, which is expected because we have over 53 uncertain variables. By the end of this exercise, you'll find out that the final probabilities of failure are 5%. On this slide is the problem statement for the uncertainty quantification. Here, we're just varying the area of each truss member, if you will. We have over 53 truss members, so there are going to be 53 uncertain variables. The starting mean is 0.01. The standard deviation is 0.0005. We're dealing with log normal distributions. Now, one of the reasons we're dealing with log normal distributions is the following. If we were dealing with log normal distribution, that actually gives you negative values sometimes. So maybe -1 as an example. We don't want negative values for the cross-section area, so we're using what's called a log normal distribution. A log normal distribution will always give you positive values. So that's why we're using the log normal distribution. Some of the quantities we want to track and monitor are the axial stresses in each of the 53 members. Some of the quantities of interest are the mean, standard deviation, more importantly, the probabilities of exceeding the bounds on the axial stresses. The bounds that we want to limit or the bounds that we want to use are the following. We want to make sure that the axial stress is between -310 and +310. Now for the optimization under uncertainty, this is the problem statement. We are going to allow the means of the truss members vary. We have these limits imposed on the OUU variables. We want to minimize the average mass in this truss, and we want to constrain the probabilities of exceeding the bounds of -310 and +310. Now, as you've seen in some of the other tutorials, we are using the MV-FOSSA method in this tutorial. I forget the name. I believe it's the mean value first order second moment method. Now, the MV-FOSSA method uses a Taylor series to approximate the responses. Since we're using an approximation to approximate the responses, the mean, standard deviation, and the probabilities, there is an error that's introduced during the OUU. So when you get the result of the OUU, you get told that this is the satisfied design. We're satisfying the constraints of 5% probability of failure. But upon confirmation, you might get a probability of failure that's actually maybe 9 or 10%. That's a problem for us. So what we do in this exercise, we knock down, we reduce the bounds from 310 to 248. I believe that's a reduction of about 20%. So because of the error introduced, because we're using the MV falsa method, we want to address that error by purposely knocking down the upper and lower bound of the axial stress constraints. So here you can see that the bounds we're using are actually negative 248 and positive 248. And here's an example of that. Here in the dotted line, or here in this first case, is where we constrain the responses to 310 and negative 310, which would be somewhere around here. Here in this blue dotted line would be the approximate distribution of one of the axial stresses when we use the MV falsa method. Now you can see that from the blue curve, we might be told, okay, there's a 5% chance of exceeding the upper bound. So there's a 5% chance here. But when we actually maybe run a sampling, maybe we run Nastran 100 times, we get that the actual distribution looks like this. I made a mistake. The orange curve would be the actual distribution. So maybe the actual distribution would tell us that, hey, you're actually violating the upper bound by 10%. So that's because there is a difference between the MV falsum predicted probability of failure and the actual probability of failure. So that's why we're knocking down. Here in the second diagram at the bottom, this is what happens when we purposely use a knockdown value. So here in this sort of yellowish line, this would be the approximate distribution. So here the approximate distribution is telling us, hey, there's a 5% chance of violating the upper bound of 248. So then when we compute the actual probabilities of failure, we find out that there is a maybe, let me look at this, a probability of failure that's actually lower than before. So let me look at this. So it might be maybe 1% would a probability, there would be a 1% probability of failure of exceeding the upper bound of 310. So you'll see this happen later on. Now here, let's see, a quick discussion on the starting location of the optimizer. So in a separate document, it's worth noting that here, just in case you haven't seen it in the other presentation, there are certain places, locations where you can start the optimizer. There is an ideal location where you want to start the optimizer. So here, let's suppose you start your OUU at the initial design. So this red box. The optimizer will try to minimize the objective function like you see here, and it'll eventually hit the OUU solution, which is currently unknown to us. The other starting location would be the location of an optimization with deterministic outputs or certain inputs. So suppose that there were no uncertainties. I just perform a traditional gradient-based optimization. So this would be this solution. After that gradient-based optimization with no uncertainty, everything's deterministic, you get this solution. You find out that this solution is close to the solution of the OUU optimization. So you notice that the distance traveled between both of these different starting locations are different. You notice that if we start at the SOL 200 solution, it has to travel a shorter distance to get to the OUU solution. Whereas if we start at the initial design, we actually have to travel a larger distance. Now, in this table, you see a summary of the differences. Suppose we start at the original values for the OUU variables, 0.01. We need over 340 Nastran runs. We need to travel along the design space. We have to run Nastran 340 times to get to the OUU solution. On the other hand, if we start the optimization at the optimal SOL 200 solution, we only have to run Nastran 282 times. And we actually get a better objective. Now, when we start at the non-ideal location in the design space, we get an objective of about 400 units of mass. But here, when we use the better starting location, we get an objective of about 190. Now, some of you might be asking, how come we don't get the same objective even though we started at different locations? That's because if we look at the objective function, if we start at the initial design, so this would be the initial design, this would be the X1, this might be the R1, so this is what the objective function might look like. When the optimizer starts at the initial value or initial design, it might reach the first nearby optimal solution. So this is one of many optimal solutions. Whereas if we start at the SOL 200 solution, which might be here, this dot, as it's trying to look for the optimal OUU solution, it's actually found a better optimum solution. So here you can imagine that the mass here might be 190, but the mass up here might be 403. So it's just the optimizer is finding the first optimal solution that it finds. So that explains the difference. Okay, just in case you're new to uncertainty quantification or optimization under uncertainty, you're using Sandia, Dakota, and you're using MSC Nastran, you're always welcome to contact me at this email address, and I'd be more than glad to have a discussion about your questions. Now, let's go ahead and move on to the first part of this tutorial. So I think I'll be jumping back and forth with the tutorial file. And so one of the first things we need is a clean downloads directory. We want to make sure we don't confuse ourselves with other files. The downloads directory is going to contain a lot of the files we work with today. And the bulk data file for that truss is going to be in the tutorial section. So let's go ahead and find that tutorial. So that would be this example here. Let's download the starting files. Now, I'm skipping one very important step. I'm assuming that you've already created your truss model. You've already analyzed it with SOL 101, the linear static solution sequence. You've already created your elements, your mouse, your nodes. Everything that you need has already been created. Also, I'm skipping the part where you configure the bulk data files for SOL 200. You've already configured the objective, the design variables for each truss member, and so on and so on. You've already defined the constraints for the axial stresses. Now, the reason we need SOL 200 is because we need Nastran to output the gradients. So I'm assuming this has already been done. Some of the other tutorials walk you through the procedure of creating the SOL 200 bulk data files and outputting the gradients. Now, one thing you want to do to this file, you want to make sure that you're outputting gradients for a lot of responses. By default, the D screen entry is going to output, I think, gradients for at most 10 responses. But here we increase the value to 100. We tell Nastran, hey, get me gradients for at least 100 responses for each different response type. And now we've already performed the optimization. And before we do that, let's make sure the DSA-PRT command is on. Okay, so we'll need to modify this in a moment. So if we look here, we have the optimal solution from SOL 200. So this is going to be the ideal starting location for the OUU. So we'll go ahead and copy those files to a different text file. Now here, let's go ahead and turn on sensitivity analysis. The way you enable sensitivity analysis, you turn it on, is by enabling this command dsaprt. Now if I go and I run that set of bulk data files, you notice that I'm only going to get gradients in the F06 file. So let's go ahead and look at that. Oh, and it seems like there is a problem with my licensing. So let's go ahead and see if I can figure this out. Let me pause the video because I think I need to restart my license server. Okay, I restarted my license server. Let's try this again. Sometimes what happens when you run Nastran hundreds or thousands of times, one of those executions holds the license and doesn't release it. So let's go ahead and look in the F06 file and see if we get results here. Let me close this and reopen this. Okay, perfect. So now I'm getting the necessary data. If we go to the very end, let me look at this. I think there's a small challenge here. Let me pause the video again and see what's going on. Okay, my apologies for the confusion. So the cause of that problem was the following. I submitted a odd configuration here. What I had in this command, I have the fully stressed design option on FSD max equals 10. That was causing the issue. So when you disable that, it allows the procedure to finish to completion. So let's go ahead and run that. And if we look inside the F06 file, you'll see that we now get the gradients that we need here. So here are the tables for all the different gradients. More importantly, the gradients are now available in the H5 file, and this is what we want. Now here, I already have a configuration for this. If we look here, I've already gone through the process of configuring part of the uncertainty quantification rather. Let me show you what I mean by this. If I go to the machine learning web app and I open those set of files, you'll notice that all the uncertain variables, all the responses have been selected for me before. Now this was done prior to this exercise just to save some time with this tutorial. So here, if we look at the left side, we've selected all the initial values for all the variables, which are now listed here on the left and the right. We've selected the mass and the axial stresses for each truss members. Now, the reason we're skipping this is because it's sort of time consuming, and this is already covered in other tutorials. Now, what we need to do is configure the optimization under uncertainty. So for this, we are going to go ahead and select the local reliability option, and we're going to select the MV-FOSSA method. We are going to select the bi-level approach. Now, all of this should align with the exercise, so let's go ahead and make sure that's what I'm doing. So if I go here, I've selected the local reliability, the MV-FOSSA method, and the bi-level method. Now let's go ahead and configure the OUU variables. Now there are a number of variables to select. So what you can do is just click each of these buttons to mark these as OUU variables. Now there are different, properties that you can set as design variables. If this was a continuous design variable, you could just select the variable itself, but here we have uncertain variables, so we select the mean of the uncertain variables. Here you can click these buttons one by one, or you can just click this one button on, and this will go ahead and select all these different variables as OUU variables. So let's go ahead and select the mean and do this for the last page of the table. So now we've selected all of these as OUU variables. Now, there are a lot of inputs, so you can go and type in the lower and the upper bound, but again, we're going to do this in a faster way. So I see that we have 4 leading zeros, so let's go ahead and type in this 0.1234 and then 1, and the upper bound is 1.0. Now you can go input by input typing all of these, or you can use this batch option. So here we'll go ahead and type in the value here and here. Now, whatever's in this input box is going to be carried over to every visible row. And so that saves us more time when it comes to configuring this. Now, whatever's visible has been updated. So if you go to the second page of this table, these values were not updated because they were not visible during the first operation. So now let's carry over those bounds. And now all the variables from X to X53 have been updated. So let's go ahead and go back to 10 rows for that page. Now, for the initial values, remember that we took the SOL 200 solution and we're using that as a starting point. So what we're going to do is we're just going to copy and paste each initial value. And you can see already that this is going to be a very time-consuming process. Here on the right is the current configuration for Dakota. So let's go ahead and copy that to a different notepad file. So you can see that the initial point keyword, this is specifying all the initial values for all 53 OUU variables. What I'm going to do later on, I'm just going to concatenate all these different design variable values, and I'm just going to replace whatever was here. So instead of that, we're going to redefine the initial point keyword, and I'm just going to paste all the initial values. So again, instead of having to type in all these values manually, at the very end, I'm going to make this edit. So we'll go ahead and skip updating the initial values for each variable for now. Okay then, so let's go ahead and move on in this exercise. Let's talk about the OUU constraints. So in a previous tutorial, I mentioned that if you use a local reliability method like the MV FALSA method, the optimizer converges faster if you use reliability indices instead of probabilities. So here we're going to constrain equivalent reliability indices. Here, let's go ahead and maybe display 50 rows in this table. You notice here for the lower and the upper bound, instead of constraining the axial stresses within negative 310 and positive 310, we knocked down the bounds to negative 248 and positive 248. Again, because the MV FALSA method introduces an error in the probabilities, we're purposely narrowing the bounds. Now here for the lower and the upper bound, let me make sure I'm using 5% for the probabilities, right? So let's go ahead and quickly apply these bounds to every row. Now, very important, when you do this, it's going to apply probability of failure to the weight response. The weight is the objective, it's not a constraint. So let's go ahead and make sure row 1 for response R1 is blank. So let's go ahead and delete that assignment for both the lower and the upper probabilities of failure. So let's go ahead and do that. So again, row 1, the mean for the mass should be blank. And you notice every other row has a 5% probability of failure assigned to the lower and the upper bound of the axial stress. Now, this only happens to every visible row, so we have to go to page 2 and redo the process. Let's go ahead and carry over the 5% for the lower bound and the 5% for the upper probability of failure. And we'll go ahead and do this for the next page, which is page 3 of this table. And you notice that internally, the web app is creating all the necessary constraints. And in a moment, I'll show you what I mean by that. Actually, I think you can tell here on the right, we get a big matrix of constants for the secondary response mapping keyword. So all these zeros have scale factors of 1. So you notice there's a 1 here, and so on and so on. These are the scale factors. This is the matrix defining your probabilities of failure. Here on the left in page 3 of the table, Let's go ahead and make sure that all of these have probabilities of failure. Now, one count we should make. Here, I believe we have over, let's do a quick addition. We have 53 constraints, and we have a constraint for the lower and the upper bound. So we should have 106 rows in this matrix. So let's go ahead and look at this. So let's go ahead and select all these different rows. We'll go ahead and copy and paste that into a text editor. And we actually have a lot more. So let me see what's going on here. I think we have double. Actually have double. So let me see what's going on. Okay, I know what's going on. We have two load cases. So we have two load cases times 53 stress values times a lower and an upper bound, so two quantities, and we'll get over 212 rows in this matrix. So that explains all the 212 rows in this big matrix of zeros and ones. Now, what this is doing, every time you supply a probability of failure here, internally it's automatically creating the constraints for you. It's automatically building this matrix for you. One last thing we have to do here, we have to select an objective. So let's go ahead and select the average mass as the objective. We want to minimize the mass, so we use a positive value here. If you wanted to maximize the objective, you would use a scale factor of -1, but here we want to minimize the objective, so we use a scale factor of 1, positive 1. Okay, so let me glance through the slides just to make sure everything looks okay. Okay, everything looks like it's going according to plan. Here, we're going to make some modifications to the optimization. So here, sometimes the optimizer will drag on. This could be because the convergence tolerance is too strict. You could alleviate or address this by terminating the optimization after a certain number of cycles. So what we can do here, we can go to the Dakota method section. So let's go to method. We are going to turn on the max iterations. From previous experience, we know that after about 10 design cycles, there's really no improvement in the optimization. So we say, hey, don't waste any more design cycles, terminate at 10. If you're repeating this exercise, maybe it might be worth terminating after 20. But given how expensive this optimization is, I think we'll terminate it at 10. One other option to control this is a convergence tolerance option here. Here we're using, I believe, 0.01. Now, you really don't know what the best convergence tolerance is beforehand. So maybe the better approach is not to consider the convergence tolerance, just focus on the max iterations. And I think for this exercise, I'll do that. I'll ignore the convergence tolerance. I'll assume we don't know what the best convergence tolerance is. I'll just assume that, hey, you know what? I know that after 10 cycles, there's really no improvement. So we'll go ahead and stop the optimization after 10. Okay, then let's go ahead and now download our new set of bulk data files and Dakota input file. So we'll go ahead and jump to the downloads directory and we'll get a new set. Now, while we're doing this, we need to update one of the keywords. Remember that we didn't update each initial value for the OUU variables. It was going to be too time consuming for us to do that. And no one wants to watch me do that for about an hour. So there's a faster way to update all those design variables. Let's go ahead and extract the contents and open the Dakota input file. So if we do that, we'll find the keyword initial point. So if we scroll down here, you could search the file for that. Here's that keyword. you notice that we did update the first 3 initial values, but for the remaining 50 variables, we left it as the default 0.01. But we don't want to start at 0.01. We want to start at these ideal initial values that we got from a SOL 200 optimization. So this is what we can do. We can take all the files and join them together. You notice that there's a space between each value. We can copy that. We can go here. Let's go ahead and delete this old set of values, and let's go ahead and paste the new set of values. So you can see that it's the initial point keyword with the first 3 initial values, and you notice that every old 0.01 value has been replaced. We're starting at the values from the SOL 200 solution. So let's go ahead and save this. And now we're ready to start the OUU. So let's go ahead and start the OUU. And let's go ahead and do that. Okay, while that's happening, let me point out that all the steps that I'm taking are in the PDF tutorial. So if you're watching this for the first time on YouTube, just be aware that there is a PDF document with each step. Everything that I've outlined is in this tutorial. And now while this is happening, let's talk about inspecting the OUU while it's executing. So right now, Dakota is performing the OUU. If you open the command prompt, this will show you that Dakota is using the conmin optimizer. So let's go ahead and look at that. It's going through the first iteration. It's running Nastran between each iteration. And you can look at the command prompt for this information, or you can look at this file, the Dakota console output temp file. So everything that you see in the command prompt should be listed here. You'll see that Dakota has run Nastran one time. It started the optimizer, and anytime the optimizer needs responses and gradients, it's running Nastran again. So this is going to happen over 200 times. This exercise is considering more than 50 uncertain variables. One thing you'll notice with a lot of other tutorials is the following. They'll maybe do the tutorial for maybe 2 or 3 variables, but then that's not okay for us. We as engineers are going to have hundreds, maybe thousands of design variables. So I wanted to show you what it looks like when you're dealing with more than 50 design variables. Another thing you'll notice in this exercise, we're considering 2 load cases or subcases 1 and 2. A lot of other tutorials show you what the process is like for just 1 subcase, but here I wanted to show you what the process is like for 2 load cases. Let's go through the tutorial and see what else I have to discuss. One thing you'll notice happened to the objective. The objective is actually increased. So I think right now it'd be worth talking about why is the mass increase. So this is discussed in some of the other tutorials I've done. In this tutorial, let's see if we can find it. There is a diagram that shows you an example. So here, that's what I'm looking for right now. This diagram. So I'll be slide 46 of this tutorial. So let's suppose we have the response function for the objective. It's in terms of just 1 variable, and here along the vertical axis is maybe the weight or some other objective function. So let's suppose we start the optimization here at the initial value. So here are the initial values for the means of the cross-section areas was 0.01. Now, when the optimizer starts for OUU, it's going to travel across the design space. Eventually, it gets to the region where the OUU solution is, and maybe the OUU solution is here, this red dot. Now, the alternative starting point is as follows. we do not perform an optimization with randomness in the inputs or the outputs. We just assume everything is deterministic. There's no uncertainty. There's no randomness. We use Nastran Sol 200 to just perform a simple optimization. We vary the cross-section areas of all 53 truss members. We make sure the axial stresses are within the lower and the upper bound. We get maybe this solution. This solution, when you look at the probability of failure, maybe there's a 66% probability of exceeding the bounds when you take into account the uncertainties and the variables. But there's one big difference in both of these starting points. You find out that the Sol 200 solution is actually closer to the region of the OU solution. Now, that's very important for us because we want to do the OU as fast as possible. And we don't want to run the FEA solver too many times. The FEA solver might take 1 hour or days to run just one time. We want to minimize the number of Nastran runs as much as possible. So what we did here, we started the OUU at the Sol 200 solution. So then it has to travel a fewer distance to the region of the OUU solution. Now, a problem with this is that the probability of failure for the initial Sol 200 solution is high. In this case, it's 66%. And I know it's 66% because I already did a sampling run. I ran this for maybe 100 or 200 Nastran runs, and I calculated what the probability of failure is. Here you notice that since the design is infeasible, we're violating the probability of failure of 5%. The optimizer has to actually increase the size of the truss members. It actually has to increase the mass a little. So that's what you see here in the final objective. We don't know what the final objective is because currently the OUU is running in the background. I think right now it'd be a good time to look at where we're at with the optimization. So if we look at this other file, the Dakota out file, this will give us some output from Dakota. So you see here at the start of the optimization, iteration 1, if you will, we have the initial values for the variables or the OUU variables. Here we see Dakota running Nastran, the blocking fork. That's indication that Dakota is running the black box function. After the black box function or MSC Nastran is finished, the responses and the gradients are recovered. You'll see that the gradients are here enclosed in brackets and labeled with R1 gradient. So gradients for response R1, R2, and so on and so on. And then feeds this information to the optimizer, and then the optimizer is iterating again between Nastran and itself. And here, if we look at the very end, we'll get some more information on where we're at. So again, it's running Nastran. Nastran is running, and here you see that we're currently at the 39th, I believe, Nastran run. One way you can count the number of Nastran runs is as following. Go back to this console output text file and look for a unique keyword that is at the beginning of each Nastran run. Each Nastran run starts with the version number, so maybe we'll go ahead and search this whole file for that keyword. And you'll notice that right now we have executed Nastran 45 times. When this tutorial was performed before, we run Nastran over 282 times. So I think, let me do this. I think it would be good to maybe pause the video here and just let that finish. Let the OUU finish before I go any further. You know, I was looking at these results of the OUU that I performed before, and I noticed the wall clock here, 1,262 seconds. I think that's about 20 minutes. So I'm not going to sit here for 20 minutes waiting for this to finish. What I'm going to do is take the existing solution files, and we'll go ahead and use that for the remainder of the discussion. So I'll still leave this running in the background. Maybe at some point during our discussion it will finish. In these solution files, you'll find, well, we'll see if we actually do have access to that. Okay, yeah. So inside of here, let's go ahead and wait a few moments for this to extract the contents. So these files are going to be the solution PDF files link that you have on that exercise. Download that set of files, look inside, and what you find inside are the known to work files. So these are the files I created before. Also included are the result files. If you look here, inside of the Dakota.help file, it's going to be the output results from that OUU that I performed before. Let's just go ahead and maybe look at this. So if you look at the very end, you get a summary of the OUU. Here in this case, it took 1,000 seconds, right? And let's go ahead and look at some of the final data. So here, towards the end, you get this section, function evaluation summary. The optimizer has acquired responses or gradients 284 times. Now, you might be tempted to say that Nastran was executed 284 times, but the number is slightly different. Here in parentheses, it tells you the actual number of Nastran runs. 282 new runs. So it's run Nastran 282 times. Now, two of the 284 were duplicates. That means that the optimizer has already evaluated two of the designs. So instead of running Nastran 2 additional times, it's just recycle the existing data. So even though it's requested responses and gradients 284 times, 282 of those were unique designs. Here you get the parameters, the objective, and the constraint values. Now, interpreting this data in the text file is a little difficult, so there is an alternative. Let's go ahead and navigate to a different web app called the Dakota Results web app. Now, I believe the way you get to this web app is by going to the home page and going to the full list of web apps. Here's somewhere. Let's go ahead and navigate through this. There's the Sandia Dakota set of web applications. You click on the Dakota Results web app, and that would take you to this link. Let's go ahead and take that Dakota Results text file and let's upload it. So here, let's go ahead and look for that Dakota Results. And since the file extension is a little different, we're going to select all files here in the bottom right so we can see all the files. Let's upload it. Now this is going to go ahead and parse this text file. And the same results that we saw here in the text file are listed in this table. So to confirm this, let's go ahead and look for the objective. So you see the objective is 189.57. That's the same objective that's listed here in the table. Maybe let's zoom in a little. Here in this next table of the constraints, these are the reliability indices and the corresponding lower and upper bound for the reliability indices. Now, we want to look at this in terms of probability. If you click the display additional columns button, this gives you additional columns. Here we have the actual probabilities of survival and failure. Now that's one of the things that you have when you work with Dakota. Whether you're using cumulative distribution function values or complementary values, you're going to get a mix of survival and failure values for both the lower and the upper bound. You can click this button and then it puts everything in terms of failure. So now we're looking at probabilities of failure. You can see that for the lower bound, there's a 0% chance of failing. For the upper bound, we actually get a very small value, 1 times 10 to the negative 9. This is effectively 0, so supposedly there's a 0% chance of failing here also. So you can look at each one and you can see what the probabilities are. Now, if you want to find the worst case probability of failure, here in the descriptor column in the search box, look for the asterisk character. This is going to show you the worst probabilities of failure, worst case probabilities of failure. We find out that responses 55, 63, 67, 78 have the worst probabilities of failure. If you look here at the probability of failure, the probability of failure is actually 4.73%, which is still within the 5% bound that we specified. Now, these are separate probabilities of failure for the lower and the upper bound. This next table tells you the combined probability of failure. So here, let's look for the asterisk. And here we get told the total combined probability of failure. The probability of survival that you're within the lower and the upper bound is 95.27%. And that happens to be the case for the other responses. The corresponding probabilities of failure are 4.73%. Now, these probabilities are approximate. We use the MV Folsom method to approximate the statistics of the responses. We approximated the mean, standard deviation, and the probabilities of failure. We need to confirm these values are actually yielding probabilities of failure less than 5%. So this is what we're going to do. We are going to take these optimal values for the design variables. So let's go ahead and copy this to a different window. So these are the optimal values. We are going to go back to that OUU that we configured. So let's go ahead and reset maybe the size, go back to Dakota. Let's change the UQ method to sampling. Sampling like Monte Carlo or land hypercube sampling, sampling with Monte Carlo or land hypercube, this would give you the most reliable mean, standard deviations, or probabilities of failure. So that's the UQ method we're going to switch to. We are now going to perform a verification. Do we actually have probabilities of failure that are less than 5%? For the OUU, we're going to select the nested OUU option. So let's go ahead and select OUU. And we want to run this OUU for just one design cycle. So if we go to method, and for the max function evaluations, we're going to say 1. Now, whenever you switch one of these options, UQ method or OUU approach, this resets the settings here in the methods section. So just keep that in mind. So if we go back to the wizard, let's go ahead and modify a few things. The starting values. So now you have to go ahead and copy and paste each initial value. But from before, we know that this is a very time-consuming process. So we could do the following. We can just make all of these values in one line, and then at the beginning specify the initial point keyword, and make sure you spell this correctly. And so now this one line has all the initial values. We'll do a copy and replace later on. Now, for the next table, the OUU constraints, since we want to verify the probabilities of failure for the original response bounds, we need to update these values. So I believe the original bounds were negative 310 E6 and positive 310 E6. So let's go ahead and do that for this part of the table. And we'll go ahead and do that for the upper bound too. Now, my desktop, it's running a little slow because this Windows operating system, it's actually a virtual machine with I think 2 gigabytes of memory and 2 cores. So they're going to be, and I'm running Nastran so many times in the background. So this virtual machine is going to be running a little slow while I'm going through the exercise. So I just wanted to point that out, just in case you're wondering why are some of the steps taking a while. I'm really tempted to shut down Nastran running in the background. Might decide that in a moment. Okay, so we did this for this set of rows. Now we have to do this for the second page of this table. So we'll go ahead and carry over the lower bound of negative 310 E6. And while that's happening, let me close this other PowerPoint just to save some memory. Let me flip through the PowerPoint slides just to make sure I'm following the procedure. We select the sampling. We're using the nested OUU approach. We've carried over some of the initial values from the OUU. Right now we're updating the lower and the upper bound. We have to do this for each page of the table. So let's go ahead and see where we're at. Okay, so we're doing this now for the upper bound. So we're carrying over the 310 to each row. Let's go ahead and see what's next. Right, so we modified the number of function evaluations. The idea is this. We want to run the optimization procedure one time and quit. The reason we're doing that is because we want to calculate the constraint values at least one time so we can verify if we are within the 5% probability of failure or not. Now, the 5% probability of failure, most likely in your case, it's going to be different. Your probability of failure limit might be maybe 0.1 or 0.01%. The entire procedure is the same. The only thing you would change for your probability of failure, you would just change this column, probability of failure for the lower and the upper bound. You would use maybe 1% or 0.1% or 0.01% in your case. Everything else is the same. Now here I'm just carrying over the lower bound to every row that's visible, and then I'll do this for the next column, the upper bound. Now, one important reminder, keep response R1 row blank. We don't want to constrain the mass. We don't want to impose any lower or upper bounds. We don't want to impose any constraints on the probability of failure, so make sure that row is blank for now. So let's go ahead and copy it over to the next one. So here we want to make sure that this input box is also blank. Okay, so we're done configuring this verification configuration, and now let's go ahead and do one last check. Let's make sure that in the method section, the maximum number of iterations is 1. Perfect. Now for sampling, since this is verification, we want to run Nastran more than 50 times, maybe 100 or 200. We've already done a convergence study, so we kind of know about how many runs we need to converge to reliable probabilities of failure. So let's go ahead and download the newest set of Dakota output files and bulk data files. So I'm going to give this a new directory, a different name. Maybe I'll call it to verification or OUU verification. So maybe let's go ahead and type that out. OUU verification. So let's go ahead and copy that. Let's go ahead and wait until our zip file is available. Okay, so let's go ahead and rename the zip file. I never like to use spaces or parentheses or other special characters. I like to keep the file name simple, letters, numbers, underscore characters, and that's it. So let's go ahead and rename this file. And then I see the first OUU is still running in the background. Maybe we can see where we're at with this. 219, so still trying to finish. That's okay. So let's do this. Let's go ahead and output the contents of that. And remember, there's one very important edit we have to make. we want to perform the uncertainty quantification at the solution of the OUU. So right now in this other file, if you recall, I took the OUU solution, I copied over, I put all the values in one line. I think it was this line. Right. I put all the OUU solution values here. So these are the optimal variable values. And then I went through the process of putting them all in one line and putting the initial point keyword at the beginning. Now, the reason I did this is to save some time. We didn't want to do this one by one in the web app. So let's go ahead and open the newest Dakota input file. And here, let's go ahead and paste the new set of initial values. So you'll see here that at the beginning, I copied and pasted the first three initial values, or here the first two. This third value was the old value. And then I didn't do this for the other ones, 0.01, 0.01. I'll show you the table just so you follow along. So if you go to the OUU variables table, I updated this value, I updated the second value, the third value was left as is, and then 0.01, 0.01, I left the other values as is also. So now what we're going to do, we're going to delete the old line and use the new line. Now, just to make sure I've configured everything, I'm going to compare this with the known version that's working. So if you recall, I downloaded the solution files for that. So I'm just going to do a comparison with Notepad. So here we'll go ahead and say compare, and this will tell me if there's anything that's slightly different. Right, so there are some differences, but I think the differences are acceptable. Let's go ahead and look here. Okay, perfect. So everything's the same, fortunately. I've configured this properly. The only differences are as follows. Here in the solution files, I configured it to 200, but today I'm using 100. So that might be, oh, right. So here in the tutorial, I'm using 200. But when I'm doing the exercise, I specified 100. If you want, you can use 200. So let's go ahead and maybe modify that. So we go to method, and here for samples, we'll say 200. And so now we're closer to this working file. Now, one other thing, we've used the probabilities keyword value for compute. So here at the bottom left, it says compute probabilities. With the version of this example that we're doing right now, we said Dakota output reliability indices. Now, it's really up to you what you want to use for the verification. For OUU with the MV FALSA method or local reliability, my recommendation is to use the reliabilities option. But if you're just verifying, you can use the probabilities or the reliabilities option. If you're using a different type of UQ method like polynomial chaos, you can use reliabilities or probabilities, and that will have no impact on the cost of your UQ or OUU. And you'll notice that everything that happens here on the left is updated here on the right. If we go to the compute keyword, you'll notice that it now says probabilities. So here at the bottom right, you'll see that it says probabilities now. The number of samples, it now says 200. Side note, just in case you're new to Dakota, trying to understand how all these keywords are related is kind of difficult. What you can do is turn on the display branches button. This will give you branch lines. This will show you how each keyword and keyword value are associated. So here are the model keyword block. It's associated with ID model, responses pointer, variables pointer. The model type, it's associated with the nested keyword, and so on and so on. If you go down here, you'll find how all the response keywords are associated to each other. So this is very handy if you're learning Dakota and want to learn how to use it. And now let's go ahead and see where we're at. Okay, so I'm not going to go through the process of running all 100 or 200 Nastran runs for the verification. We already have the solution files in this directory. Remember, we went to the user's guide. The existing solution files were available, so we just downloaded those. And we're looking inside of the solution files. Nastran working directory 1 is the verification set of files. So if we look here, we can look in the Dakota out file. And go ahead and clean some of this up. And then if we look at the very end, we're going to get a summary of the OUU. And remember the summary, or not the summary, remember the OUU ran at least one time, one iteration, if you will. And that was just to calculate the constraint values. Here you see that it's run Nastran 200 times. So the sampling, we told it, hey, run sampling LHS or land hypercube sampling, use 200 runs. And it did that. Here the optimal parameters, since we really ran the OUU procedure one time, there's no change in the design variables, so all of this should be the same as before. The objective should be the same as before. More importantly, we wanted to know what the constraint values are. So instead of looking at that file, let's open the Dakota output file, or the Dakota results web app. And let's go ahead and upload that Dakota output file we saw a moment ago, the verification with the 200 runs. Let's see what the actual probabilities of failure are. So here, let's go ahead and select the all files option and select the dakota.out file. And now here, again, there are a lot of rows. We can just type in the asterisk. This will show us which constraint is the worst case. Let's go ahead and turn on display everything as a probability of failure. Okay, so here in this other window, let's look at response R98. Let me do this for this top table. So let's go and search this table. Okay, so during the OUU, when we use the MV falsa method, we get told that the probability of failure is 3.13%. Now, when we did the verification, we find out the actual probability of failure is 5%. So this is why if you use a local or the MV falsa method, the verification procedure is very important. You have to see what the actual probabilities of failure were. During the OUU, the MV falsa method, we were just approximating the probabilities of failure. And then here you could do this with the next table. You would look for the asterisk. R98 again is that one. If you go back to the old set of files, here again, it's the same probability. It was telling us, hey, when we approximated the statistics, we think the final probability of failure is 3.13%. But here, when we actually verify the final probability of failure, it's 5%, which is good. We still wanted a maximum of 5% probability of failure. So far, it's been a success. And let's see where this other Nastran run is at. The first OUU hasn't even finished it, so let's see where it's at. 276 runs, so I think that first OUU is almost on the verge of finishing. Just to make sure that first OUU has been configured properly, what we can do is the following. We can take the known to work input file. I selected the wrong one. We could take the known to work input file. We can open it in Notepad, so that's here on the left. And we can open the input file that we configured during this exercise. So if we look inside of this workspace D directory, here's the input file. And now we show the working file on the left from before this exercise and the input file we configured today in this exercise. And let's go ahead and compare the files. Let's see if there's anything a little different. The convergence tolerance, in this case, we're relying more on the maximum number of iterations. Here, there is a difference in the initial values, but it's not the initial values. It's just the fact that we've used a different number of spaces. So here on the left, in the other input file, we're using maybe 3 spaces, but here on the right, we're only using 1 space. So that's the only difference here. And then everything else is the same. So I expect this OUU that's currently running from 15-20 minutes ago, I expect it to finish soon. Let's go ahead and see how many runs we're at right now. So we're at 287 runs. So we still got a little bit more to go. There might be a difference in the number of Nastran runs for the following reason. Here we're already at 287 MSC Nastran runs. Keep in mind the input files are the same between the solution file and the file that we configured today. So before it was 282 Nastran runs, I believe. Let's go ahead and confirm this. Let's look in the PowerPoint. Right, 282. This OUU on the left was done on Linux with Intel Xeon processors. Now here on the right, what are we using? We're using Windows. We're actually using a virtual machine, so everything is virtual with 2 cores. Now, the fact that we're using a different operating system is going to influence the optimizer. The optimizer might take a different path in the design space and might arrive at a slightly different solution. Also, that might determine how soon you get to the OUU solution. Here, I already see that it's taking more than 282 runs, and everything else is the same. The input files are the same. The only difference is the operating system, the processors, and the amount of memory. Also here, I'm running a virtualized processor. It's not running as fast as an Intel Xeon processor. So I think these differences are going to cause the OUU to take a little longer. So let's go ahead and just pause here and wait a few moments for that to finish. Now I'm still waiting for this to finish. One thing that might be briefly going over is the appendix. Now, just in case you're new to uncertainty quantification or optimization under uncertainty, the appendix in the tutorial file has information for some of the most commonly asked questions. If you're new to Dakota and you want to learn how to interpret the Dakota input file, there's a section in the appendix for that. If you are new to interpreting the probabilities, whether they're cumulative or complementary, there are some slides explaining what the differences are between the CDF and the CCDF. There are also some slides on the definitions for probability, reliability index, and generalized reliabilities. I know most of us have worked with probabilities. We know that if you use the MV-FALSA method or local reliability for uncertainty quantification, constraining and working with reliabilities helps move the OUU faster. But many of you might not be familiar with what a reliability index is. So this set of slides talks about what a probability is and what the association is with a reliability index. So if you're new to that, here we go over what a reliability index is. Also, if you're not familiar with what a generalized reliability index is, here we define it, what it is. And then here we just go into more information that you might find useful. I recommend that before you go through this exercise, go through the appendix. Try and become familiar with some of these terms: CDF, PDF, CCDF. Be familiar with what the reliability index is. More importantly, get used to these plots. So here we have the terminology. P, the probability the random variable is less than 20,000. This is basically giving you the shaded area under the PDF curve left of 20,000. Here on the right, we're saying the probability that the random variable x, and that could be the mass, that could be the axial stress. What's the probability that the random variable x is greater than 20,000, which would be the shaded region right of that response level? Be familiar with this. This is going to help you a lot when you're going about UQ and OUU. Let's go ahead and exit here, and let's go ahead and see where we're at with the OUU that we had a moment ago. Okay, so let me pause here and let this finish. So this OUU from the very first part of this video is taking an unusually long time to converge. I took some time to look at it, and I think I have an answer as to why it's taking a long time. Remember when I said that when we compare both input files, here on the left is the known working version, here on the right is the version we configured in this tutorial. Everything was the same. The initial point keyword, the only difference here, we use a different number of spaces, but the values were the same. The only difference is the convergence tolerance. That's where the mistake was. What I should have done, I should have modified the convergence tolerance to something like this. So convergence tolerance should have been something like this. Let's go ahead and say 0.01. Now, the default, I believe, is this. 1 times 10 to the negative 4, or 0.0001. Now, with this default convergence tolerance, the optimizer is running multiple times just to converge. Here, if we go to the Dakota console output text file, if you look for this keyword iter, it will show you that right now we're at the 7th iteration, but if you look carefully at the objective values, we're not really improving the design anymore. What I should have done is the following. Let's go ahead and go back to here. I should have either used a convergence tolerance of 0.01, or I should have used a maximum number of iterations of 5. I think 5 might have been the better thing to do. So you know what? This is what I'll do. I'll do 5 here. So let's go ahead and find 5. Right, so here, let's go ahead and make this 5. Just so in the future, everyone knows that it's 5 instead of 10. So maybe we'll go back here. And I don't know if this will work, but we'll see. Oh, you know what? I'll just take a shortcut. Let's just go ahead and put a 5 here. So instead of retaking the whole screenshot, I'm just going to say 5 here. Let's go ahead and reduce the size and something like that. So 5 here, set to indicate it. 5 here. Okay, perfect. So we'll go ahead and save that. And now I'm going to terminate this OUU. Again, the reason this OUU is still in the process, it's because the default convergence tolerance is very small. I think this or this might be the default tolerance. So the optimizer is just running endlessly trying to converge to this tolerance. But we see from the OUU progress, here's the OUU progress. If you look at the objective, after about 5 iterations, it's no longer improving the design. So we could do this. We could say terminate after 5 iterations. or use a convergence tolerance of 0.01. Here, I think the better approach might be to set it to max iterations equals to 5. So that's what we did. We said make max iterations 5. So if you do that, you should be able to replicate the results in this exercise. My apologies that took longer than I was expecting. It's very interesting that it just takes one small value and now your optimization behaves completely different. So that's why we have this tutorial file with explicit instructions on how to go about this exercise. I recommend going step by step with this exercise. Try to match as many values as you can, and you should see that your results are identical or nearly identical to the results that you see in this exercise. So with that, I'll stop here. As always, you have questions or comments, my email address is here at the bottom. You're always more than welcome to contact me, and I'll get back to you as soon as I can. Thank you.